Alright, so this is my Lab4 code. I'm briefly going to go through my Arduino code before I show you the screenshots that I got. So here at the beginning, I'm initializing my T, which I'll use later down here to get the sampling rate. So I just initialized the serial, which was specified, as well as both of the pin modes to specify those as inputs that will be used later. And then in the loop, I am taking my F sample through the analog read A2, which is connected to the potentiometer. And then the output is connected to the Nscope board, which will be read into the serial print as a string so that it can be put into the processing code. Then my delay microseconds, I initially used regular delay, but it was not sampling very well, so I changed that to a delay microseconds. And then multiplied my time by 1000 in there to make sure it was correct. So now I'm going to pull up my screenshots. So I'm just going to scroll through these really quickly. And here's the last ones at 100. And notice that I included in my screenshot in the background property of Joe Culver, just to make sure that they are my own. And next I'm going to show you guys my table. Hold on, let me pull my... Yes, so next we're going to show the table. And so what I did to find the aliasing was I used this formula. This is what we talked about in the lecture as far as finding the nearest integer of this ratio, multiplying it by sampling frequency, and then I used this absolute value to make sure that it was a positive integer. So this is a look at my whole table. And one interesting thing I would like to note is that the 142s were actually the ones that I found the most variation in between all of the frequencies, which is interesting because 142 is the one I actually got to be perfectly exact compared to the other ones. So I guess it was just a little miscommunication between the sampling. This could also be due to the fact that I wasn't able to achieve the full 5 volts amplitude because of the Arduino, but nonetheless, it was still giving me very close values, so I took those to be accurate. Okay, so now I'm going to demonstrate the triangle and square wave. So the first one was a square wave. I had to change this to the pulse output at 10 hertz due to the fact that that is what would create a square wave, and so I switched that to the pulse in my Nscope. And then pulling this up, I found this result. This is actually similar to what we found in class where, as you can see, there's frequencies heading to basically infinity. This is due to the fact that it is extremely hard to achieve this flat top due to the sine wave nature, since it is going up and down. And so we would expect to see frequencies going further into the future. So I cut that last video just so I could switch my Nscope around. Now I'm looking at the analog output so I could create a triangle wave. And here I switched it back into analog 1. And then going into the processing, I'm going to run it again. And as you can see, it's creating the triangle wave. And this does not have frequencies going further and further. This is because it is easy for the Fourier to mimic the triangle wave due to the up and down, which is very similar to the sine wave. So yeah, but that is the triangle wave with the corresponding frequency diagram.